My name is SunWoo Kim from Hanyang University. Today I'm going to talk about the seminar with the title Integrated Sensing, Localization and Communication for 6G. As you probably know, the localization and positioning becomes increasingly important for various applications in 5G. So today I hope this talk provides a quick overview on how localization techniques are currently developing and also how it is extended for the environment sensing. And most importantly, I'm going to give you some messages regarding the integrated design of localization, sensing, and communication. Let me first start with a brief introduction of localization. As you know, the wireless localization, which is sometimes called positioning, geolocation, or radiolocation, is to identify the location of sensors, mobiles, and various objects with the assistance of wireless communication systems. And of course, the global positioning system, which is one type of satellite navigation system, would be the most well-known technology. However, the fact that the satellite navigation signal does not penetrate indoor creates necessities of terrestrial network-based localization systems, which is roughly started developing in the end of 1990s when the US FCC enforced E911 to the wireless service providers in US. Since then, the various wireless positioning and localization techniques have been developed for both indoor and outdoor, and they use all kinds of wireless signals existing like WLAN, cellular signals, and Bluetooth, and so on. Nowadays, the navigation with the terrestrial network becomes a strong alternative to the satellite navigation system. And we are expecting the future 6G wireless network will need these wireless positioning localization technologies very much, especially for the application of self-driving cars, robots, drones with high mobility. And as you see in the figure, the positioning and communication can benefit from each other. Good positioning will be able to assist communication, and the improved communication can help positioning as well. And this is what we call location awareness in communication. And if we can integrate these two separate functions into a single system, the communication system can be drastically enhanced, especially in the case of future 6G systems. Furthermore, now it is understood that the 6G signals we are expecting not only high precision localization, but also environment sensing with the assistance of high performance receiver processing. Here by environment sensing, we are referring to estimating the presence, motion, activity of various objects in the vicinity of the TX and RX. And these facts have been already envisioned in the white paper by 6G research group in Europe in 2020. Historically, sensing and communication have been designed separately. For example, radar system, which is a typical form of wireless sensing, and communication system have been considered a bit different areas. The different people worked on each one of them. But in 6G, dynamic deployment of networks for various unmanned systems, high mobility devices, dense network scenarios is calling for high performance localization and sensing techniques. And it becomes indispensable to have integrated design of sensing and communication for 6G networks. Although the effort to combine these two functions is not totally new, the term ISAC is gaining a significant attention in the 6G research and development. Especially the highly capable positioning and sensing techniques, which will provide up to centimeter level accuracy, is a powerful driving force for the integrated sensing and communication. To understand the situation better, here I'm going to show you the reasons why the localization becomes promising in beyond 5G and 6G wireless networks. First, high carrier frequency yield high directivity transmission property and decreases the size of antenna array with the reduced size of wavelengths. And large bandwidth allows the enhanced time delay resolution and delay estimation accuracy. Third, the large number of antenna elements can be packed in the system, which yields very accurate angle estimation. And D2D communication is also an important feature in 6G, which provides a large number of measurements between UEs and improves coverage and accuracy. Similarly, highly dense network will increase the probability of line-of-sight link, which is always beneficial for the improved localization. Currently, various techniques are being considered in beyond 5G and 6G wireless networks. For example, there exists the downlink and uplink TDOA and AOA method, and multi-RTT, which is multi-cell round-trip time, is also being introduced in the 3GPP standard. Bluetooth and Wi-Fi signals can also be used as beacon signals along with the cellular positioning. RSSI, CSI pattern matching is another good option for positioning in 5G, 6G, which has been well investigated for a while with WLAN signal. Another option would be the one called range-free localization, in which connectivity information between devices are exploited for localization in a dense network. Assisted GNSS and enhanced stellar ID is also usual suspect in 5G, 6G localization. On top of that, we are also envisioning the environmental sensing with 6G signal. And localization with reconfigurable intelligent surface is recently becoming a hot topic in the field as well. Now in this slide, I'd like to explain how this localization can be further extended towards wireless sensing. Historically, non-line of sight path has been a chronic problem in localization for a long time. However, with the improved signal processing capacity of the system, it will be no longer the chronic problem. Rather, it is becoming a useful information for wireless sensing. To explain this better, it is because the multipath channel is the result of propagation environment, and the multipath channel effectively describes the surrounding environment. As you see in the figure, the multipath of this reflective path is caused by nearby buildings or various types of surrounding objects. If you can estimate time delays and angle arrival or departure of those multipaths accurately, constructing the shape of the surrounding environment may be possible. This is the basic principle explaining how the wireless sensing becomes possible in the future 6G communication. Of course, this requires high multipath resolution, and strong signal processing techniques are needed to acquire channel parameter estimate. But I believe this will gradually be achievable in preparation of 6G communication. As a first interesting example of the advanced sensing technology with 6G signal, I'd like to talk about radio-based simultaneous localization and mapping technology. In short, we call it SLAM. The SLAM is mostly well known as a visual SLAM or vision LiDAR SLAM in the robotic field. According to Wikipedia, it is constructing or updating a map of an unknown environment while simultaneously keeping track of an agent's location. Basically, it is based on using visible light. So as you see in this figure, one vehicle equipped with the camera or LiDAR moves around on the floor and constructs the flow map and its location. The important observation we can make here is that in the future wireless networks, the radio frequency is increasing. and the property of the communication signals becomes very similar to those of visible light. So as I mentioned earlier, for example, the directivity and reflectivity becomes stronger. Therefore, if we use these properties, it is natural to think that something like vision slam becomes possible with the communication signal. Now, the new technology called Radioslam starts being studied in the communication field. And soon it will be feasible with the use of 5G millimeter wave signal or 6G terahertz signals with corresponding sensing resolutions. To explain further about Radioslam, we can split it into two parts, localization part and mapping part. In localization part, we want to estimate the location of UE given the map of physical environment. In mapping part, we want to estimate or sense the location of reflection and scattering points between base station and the UE given the location of UE. They iteratively running so that the map and the UE locations are updated one by one. In this case, the UE is working as a sensor. When the UE receives the signal within the field of view, it can sense or identify the existence of a landmark or any object in it. So in the Radioslam, the location of objects are usually expressed as probability density functions, and our goal is to estimate the vehicle or UE state and build up the map of the propagation environment, which consists of various landmarks and scattering points. So for example, the basic routine would be like, first, the base station transmits the 5G millimeter wave signals, and they are reflected by various reflecting surfaces or scattered by the scattering point. Then there will be multipaths from base station to UE, or vehicle in this case, and which include reflected path, scattered path, and direct path from BS to the vehicle. In this scenario, the UE runs some appropriate signal processing algorithms to estimate the path delays and angle arrival and departure. And now, note that these delays and angles are geometrically and functionally related to the environment. Therefore, as we have those channel parameter estimates, we'll be able to get the environment information, which is basically environment sensing, and also very similar to the function of conventional radar system. Let's look at the simple graphical interpretation of this Radioslam. Here we have the base station at the center, which transmits the signal to the vehicle, and the vehicle is circulating around the base station. The red lines are the paths reflected by the wall, and the blue line is the path scattered by the scattering point. When those paths are received by the vehicle, then with the Radioslam algorithm, the reflecting surfaces and scattering points are revealed and marked pink and red. And this is a simple animation showing how this Radioslam can work in the wireless network. And now, as you see, this Radioslam has a great potential for the use of environment sensing with the upcoming high-frequency 6G signals. And it is definitely a key example of ISAC. It will also have a wide range of application in autonomous driving systems, unmanned systems like drones, robots, and partly can replace the role of vision slam when you need a certain level of privacy that can be harmed by the camera. We'll have the improved sensing capability with increasing signal frequency, and high performance signal processing techniques, including AI, will further advance this technology. Now I'm going to spend a couple of slides to talk about vision-aided beam management. Well, as you know, in 6G, the signal frequency goes up, and we actively use the fine and narrow beams. And at the same time, devices are moving fast with drones and cars. Now the question is how we can handle and maintain the communication link when beams are sharp and devices are moving fast. We've been studying this problem in the past few years, and it seems like this problem is actually very difficult if you only rely on the conventional communication algorithms. For instance, we typically can do sort of hierarchical beam alignment in the early stage of access. Then we can do, when things start moving, we can use extended Kalman filter or particle filter for beam tracking. But in general, from the experience, depending on the level of beam size and the degree of mobility, the problem can be very harsh. Luckily these days, if you look around, there are various sensors, and anyone can think using these various sensors for this purpose. So there comes the vision-aided beam management. Using vision or camera image can make this troublesome beam management very simple and effective. You can install camera at the transmitter, and the transmitter can instantly know where to transmit. It is actually very simple, but was easily neglected in the past. So in the upcoming 6G era, we consider combining this approach into the communication system, and that will be another Isaac example. Let's take a look at the details of the vision-aided beam management tracking. First, the system checks the RX locations or direction toward RX with the help of well-known object detection algorithm called YOLO. After the target objects are detected from the image, we estimate the angle to them and decide what beam index we will use based on this information. Lastly, the system performs TX and RX beam alignment by sharing the beam index information between them. If the RX and TX move, the image instantly tells you the direction, and accordingly the system can adjust the beam directions. The image on the right side presents the prototype of our vision-aided beam tracking system recently shown in the ACM conference. To conclude, I'd like to emphasize that the communication is now more than data transmission. The localization is being extended to the level of environment sensing, and the wireless communication will be a great tool for us to understand the environment in the 6G era. Also, it will be essential to have the integrated design of localization, sensing, and communication. And those dynamic interplay between them will further improve the next generation communication system. And of course, there exists quite a lot of technical challenges regarding the signal processing algorithm design, transmission signal design, hardware issues, fundamental theories, and so on. But I'm sure as we put our efforts together in solving these problems, the 6G system will become more intelligent and autonomous. And hopefully it will bring us a bright and enjoyable future. Thank you very much.